Okay, so we've practiced with finding the equilibrium concentrations and the equilibrium constant when given the initial and one equilibrium concentration. Now what we need to do is figure out if we are not given the equilibrium concentrations, but we're given a K value, can we figure out the equilibrium concentrations? The backwards of what we just did, or the opposite end of our spectrum. We are still going to be using an ice table. What we need to do is when we start, we need to decide in which direction we are going to proceed. We got to compare Q to K so that we know which way we are going to go. Sometimes this is easy. Sometimes it's straightforward. Sometimes it's not. Define the changes for all the materials in terms of X using the balanced chemical equation. Do not forget those coefficients in our C of our ice table in the change row. The X change is plus for materials on the side of the reaction that it's proceeding towards. So if we're making more products, products will be positive. If we're making more reactants, reactants would be positive. And the change X is negative for all the materials that we have too much of and the reaction proceeds in the opposite direction. Then we need to solve for X. When we think about solving for X, some equations that we'll be presented with will need the quadratic formula for. Some equations we can simplify and not have to use the quadratic equation. When we get to those types of finding equilibrium concentrations and the assumption rule, I will let you know what we got. Finding the equilibrium using an ice table. ICE again stands for initial concentration, change in concentration to reach equilibrium, and E, equilibrium concentrations. The ICE table organizes for us some given information in a problem requiring us to solve either the concentrations or the K value. We've already seen the K value. Now we're going to find what happens if we're not given the change in concentration and we are given a K. How can we find these concentrations? So for this reaction right here, A goes to 2B. What we can set up is if we have the initial concentration of A and the initial concentration of B, we can compare Q to the K given and see which way the reaction would go. Well, seeing that we have no product here, we're probably going to make product, which is why we slap a negative on the reactant side and a positive on the product side. We put a 2 in front of the X for the change in B because we have a 2 coefficient in front of B. What we get from the ICE table now is in E, we get a little algebraic equation. And this is what we have to plug in to our calculation for K, KC, or KP. What we're just going to generically call the KEQ, the equilibrium constant. So it's very dependent on the balanced chemical equation, the initial concentration that we're given, and the KEQ value. Let's practice. Let's say I have a reaction where N2O4 gas is in an equilibrium with a product 2NO2 gas. The Kc for this reaction is 0.36 at 100 degrees Celsius. Temperature is not important as long as we know it's kept constant. If our initial concentration of NO2, put a little 0 there for initial concentration, is 0.100 molar, and the initial concentration of N2O4 is 0 molar, we need to find the equilibrium concentrations. Now, we need to set up our ICE table. Again, we got to have rows for I, C, and E. and then a column for each of our reactants and products, N2O4 and NO2. Got an extra one, no big deal. Initially, 0 and 0.100. Our change, take a minute, predict which way are we going to go. Most likely we're going to go make reactants. We can calculate the Q, 0.100 over 0, which would be infinity. Q is greater than K, the 0.36. So we got the reverse reaction going on. We need to make reactants. Plus X minus 2X. 2 again, being from the balanced chemical equation. So our equilibrium constant for N2O4, we'll simply say is X. For NO2, it's 0.1 minus 2X. Now these are the values that we are going to put into our K. Kc is equal to 0.100 minus 2 squared over X squared. We know Kc, it's equal to 0.36. Now, lots of algebra. We need to FOIL, first, outer, inner, last. And we have this, not a square, sorry. And we have this denominator that we have to distribute over to the other side. Our goal here is to solve for X. When we have this type of setup, I'm going to switch over my Kc value here, and I'm going to start changing up my algebra. I brought the X over from the denominator, and then I'm going to distribute 0.36X is equal to 0.01, 0.1 squared minus 0.400x plus 4x squared. If you need a refresher on foiling, first, outer, inner, last, all that stuff, take a moment, let me know, we can go over it. Now, bringing these over, we have .01 minus 0.76x plus 4x squared. We have to use the quadratic equation. The quadratic equation says that x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Now that plus or minus is going to give us two values for x. One is going to work, one is not going to work. And we'll be able to plug them back in to see which one's not going to work, okay? Now, when we write this in terms of the order, x squared, x, and then no x value, this is where we're getting our A, B, and C. We'll plug those in, and what we get is x could equal 0.176, or x could equal 0.014. Which one is it? Well, plug them both in, see which one gives you a negative concentration. We don't want a negative concentration, so therefore the only one that will work is x equaling 0.014. That is our change. Then we can plug it back into our ICE table, plus 0.014 minus 2 times 0.014. and we'll solve for our equilibrium concentrations. The concentration of N2O4 is 0.014 molar. The concentration of NO2 is 0.072 molar. 0.1 minus 2 times 0.014. All right, so there's our final answer. Finding the equilibrium concentrations. If you plug in the other X value, you'll get negative equilibrium concentrations. You can't have negative. If you also plug these equilibrium concentrations back into K, you'll come up with the same K value that we already had, 0.36, 0.37, somewhere around there. Rounding errors acceptable. All right. Now, yes, I know the quadratic equation sucks. I get it. It makes sense. Using approximations, we could simplify the math using what we call the 5% rule. When the equilibrium concentration is very, very small, the position of the equilibrium favors reactants. For relatively large initial concentrations of the reactants, then the reactant concentration will not change that much. And so what we can say is, since the reactant concentration will not change significantly, we can assume the reaction is going to proceed forward, but those initial concentrations of the reactants would be the same. And so we can assume the X is going to be small and remove it from our calculation. Now, what does that look like? Glad you asked. Let's look at a different reaction. 2H2S gas react to form 2H2 gas plus S2 gas. The Kc is equal to 1.67 times 10 to the negative 7 at 800 degrees. Notice that that concentration is, that Kc value is extremely small. Reactants are favored. So if I had an initial concentration of H2S at being 0.0250 molar, what I can start to assume is whether or not this is small. We use the 5% rule, which tells us that if we were to calculate using that X value, we're going to be able to say only when we calculate without the X value, we can assume that X is going to be small. Noting that here, this is not a huge amount, but this is a very, very small amount for Kc. We're going to, at the end, check to see if our approximation was valid. So let's go ahead and make our ICE table. Again, this is a question that's asking for calculating the equilibrium concentrations of our reactants and products, given our initial concentrations and the Kc. So for H2S, we start off with 0.025. H2, we're starting with nothing, and S2, we're starting with nothing. Now, our change in concentration, again, we should be making products since we start with none, minus 2x plus 2x plus x. Again, notice the coefficients of the balanced chemical equation. There's a 1 there, understanding the 1. 0.0250 minus 2x, 2x, and x. Let's write out our Kc. 1.67 times 10 to the negative 7 is equal to 2x squared times x, the concentration of H2 squared, times the concentration of x, S2, excuse me, divided by 0.025 minus 2x squared. Do we see the problem, child? This one, that's the one that we're going to say, hey, we want to assume X is small. When it's involved in the Kc expression with an initial concentration that's not 0. Notice H2S, the reactant, the denominator. That X value is tied to an initial concentration, 0.025 minus 2X. That's the X we want to assume is small. That's the X we're going to say, bye, make it easier on us. Let's look at our expression now. 2x squared times x over 0.0250. A lot easier, right? Yeah. Well, okay, 1.67 times 10 to the negative 7 equals 4x cubed. Remember this we can do. We square the 2, that's 4. We square the x, multiply it by another x. Nice. Now solve for x. We multiply both sides. Oops, squared. Excuse me, don't drop the square. This square needs to stay there. 6.25 times 10 to the negative 4. Excellent. Now solve for x. Multiply both sides by that denominator, divide by 4, take the cube root. All right? X should equal 2.97 times 10 to the negative 4. That's the change in concentration. Let's see if we've established the 5% rule. The X divided by the initial concentration. Times 100%. If this is equal to 0.5 or less, then we can keep this X value. If it's greater than 5%, then we need to go back and do the quadratic equation. All right, 2.97 times 10 to the negative 4 over 0.0250. I'm going to go ahead and multiply by that 100% so that I can see the percentage of anything less than 5. If you don't want to do the percentage, the ratio should be less than 0.05. We get a 1.19%. Yes, X is small. And we were able to assume that small approximation, right? That idea that now we can keep this X value, right? The only way we can keep this X value is if it was established as small. If this was greater than 5%, we'd have to go back here and not assume that it's small. So now our equilibrium concentrations again. 2.97 times 10 to the negative 4, 2.97, times 2. Times 10 to the negative 4, make your ice tables bigger, and 2.97 times 10 to the negative 4. So we know the concentrations of S2, 2.97 times 10 to the negative 4 molar. 2 times that value would be 5.94 times 10 to the negative 4 molar. And the concentration now of H2S, 0.0244 molar. Awesome.